okay? But you're kind of putting the cart before the horse here. All these problems started with what? When we were finding...
Typical strips.
What's that?
Typical strips.
Typical strip.
Picture.
Okay, a picture,
Graph.
a graph.
Where
Where do these solids come from? Where do the solids come from? All these rotating what? Rotating what?
the solid around.
Think about the homework you've been doing. So where do these solids come from?
Rotating regions.
Rotating regions, right? All of these came from rotating a region, right? So what region would be rotated to form a right circular cone? What shape of a region would you rotate to form a right circular cone?
Upside down. Right triangle. Half triangle. Right triangle.
A right triangle?
Upside down.
Okay.
Yeah, I would think of y equals something like this.
Yeah, so, yep. So, like, if you think about, look at this right, and I think this, what a couple of you said. If you flip that around, wouldn't you get the volume? So that region is a right triangle. Okay, where's that right triangle going to come from?
Y equals X.
Y equals X.
Well, some linear function.
Some linear function.
Yeah, and
So some linear function, but so what linear function are we going to want? Y equals X?
X equals 0.
Okay, X equals 0, so this. So yeah, the y-axis, right? And this, whatever this line is, y equals X or something. And anything else?
Need a right bound.
A right bound? Isn't this the right bound?
Oh, yeah, I mean, well, depending on how you're looking at it, you can cut it off at the top or the right.
Oh yeah, so this will be easier. If we,
Yeah, so let's cut it off at the top.
yeah. Okay, so then we need another line up here. So maybe let's start with that one. What will that line be?
Y equals something.
Right, y equals what? No, but we're deriving the general formula for a cone. 1/3 pi r squared h.
C. A.
But we know it's not. So we don't have to. We know what it is, right? It's not r. It's not a. It's not c.
H. It's X.
Is it x?
It is X. It's Y equals X. Yeah.
Y equals x.
That's H. The Y.
Is that every right circular cone?
No.
Is that a 45-degree angle like that?
Yeah.
No. So if you do y equals x, it's only very one specific cone where its angle on its side, the lateral side, is a 45 degrees or pi over 4. But we want any possible right circular cone. So what? This is our formula that we're going after here. Then the top boundary is what? Y equals what? H. Right? So that's going to be y equals h is going to be that top thing. Okay, now let's go back to this thing. So what about this line? If we do y equals x, that's only a very specific right circular cone, but we want any right circular cone. So what is the equation of that line? Or what is it that we want that we could come up with the equation of that line?
Repeat the question.
Well, we need to figure out what is this line.
the triangle formula?
What's that?
Do we use the area of the triangle formula? Like half base height?
No, we need the equation of that line. We need the equation of that line so that this is so that when we rotate that region, we have a right circular cone with radius r and height h.
We have the
R squared?
Y equals r.
Do we need to use trigonometry?
So y equals r. Is that what you're saying? What about y equals r? Does it work? What kind of line is y equals r?
That's a constant R.
It's a constant. That'd be a horizontal line, right? So it's not y equals r.
Do we need to use trigonometry? Y equals
No.
H divided by X.
H divided by x.
Rather than around of that line.
Okay, so rather than I kind of feel like the responses are kind of like just trying to write down the answer rather than like taking baby steps to figure it out. So what do we know for sure? So we want this right triangle, or this cone, to have a height of h and a radius of r. So maybe before we just try to write down the equation, what could we know for sure in this situation? If we want the radius to be r and the height to be h.
You know the intersection?
The intersection. This one?
Yeah, we know
Okay.
that that's going to be the biggest R, comma, H.
Okay, is the coordinates of that point r, comma, h. What's the x coordinate of that point? Is it the radius of this cone that we want eventually?
Yeah.
Yeah. That's exactly what it is. That's the radius of, that's the x coordinate. It's the radius of the cone that we want. Should make sense.
So now if we have a point, we can get the equation.
Yeah, exactly. Yeah.
Solid.
Yeah, do it in baby steps. Don't just guess at the final result. We got this point RH, so then how would you find the equation of that line? It goes to the point RH, it also goes to the point 0, 0.
So we can just do mx plus b.
So now we all should be able to write the equation of that line. Anybody? Pre-algebra. H over
So
R.
just H.
She wants H over Rx. How did you get that?
I just did y2 minus
So you did the formula. Why does H over R, does H over Rx make sense?
That's the slope.
What's H over R? That's the slope, right? It's the rise per run. It's going to be H per R, right? Times X. So the equation of that line, if we want the radius of the cone that we're going to get to be R and the height of it to be H, then the equation of that line will be H over Rx. Okay, so you'll finish this for homework then. Now that's the hard part, right? That's just the easy part is now just finishing it. So prove this. And let's say we're going to use two different approaches to do it. Different approaches. So you're going to do it twice. You're going to do it twice. Okay, is the task clear?
Do small in class.
Yeah, it's homework. But the nice thing about this problem is you know when you get it right? Because we know what we're going to get in the end, right? If you do this right, you're going to calculate a volume, and your final answer should be 1/3 pi r squared h. Both ways you do it. And then if you do, then you've proven that that's the volume of a cone. Before in geometry they just gave it to you, right? But here we're saying, okay, suppose we didn't know it and we had to derive it. Well, now we have the techniques, these volume techniques are able to do it. Yeah?
So here's another thing they've just given us. Like, we know the volume of some prism, like a rectangular prism, is length, width, height, or depth, right? So we just take that for granted. But it seems like we're doing the same thing here. We're just, like, adding up all those cross sections. Like, we know the area of the face, and we're multiplying it by the length of the solid.
Here we're doing that?
No, I'm just saying, I was trying to explain it to a friend last night, and he couldn't understand the connection between, like, adding up infinitesimally small things in 2 dimensions to get a 3-dimensional thing. He couldn't make the conceptual leap. Now, granted, he wasn't here to understand, like, integration and the delta x and all that.
But they're still 3-dimensional. They're just so thin that it's indistinguishable from. But you're still thinking that that's very, very thin 3-dimensional
So then
elements.
how do we explain length with depth then? Because it seems like we're taking the area of one of the faces and multiplying it by the length. Or the depth of a rectangular prism.
Okay. I'm not sure which question is.
I'll think about it.
Yeah, but so yeah, we're doing these complicated volumes, but we have to have some basic volume facts in place to do them. I guess is what you're saying. Like length times width times height is like we just take that for granted.
I think I was incorrect when I conflated infinitesimally small to negligible. There actually is some width.
Yes. It's just so small that it would, that then the result is indistinguishable from the actual volume. Right. Okay. So let's talk about physics applications here. So one of the main keys to physics applications of these is just, again, reviewing the principle of integral in general. And that just the very basic idea of an integral is what? So every time we've done an integral, it's had the same kind of general meaning. And what was that general meaning? Sum up. What's that? Okay, we sum up. Bits of a quantity Q. And what does that give us when we do that? Right, the total change of Q, or the total accumulated amount of Q. So all these geometry applications are no different. Right? We summed up volumes of elements, volumes of typical elements, right? whether that was a washer or a disc or a pancake or a shell. We're summing up the volumes of all these typical elements, and what do we get? Total volume of the solid that we formed, right? So this principle, just every time we do an integral, this is the principle that applies. We're summing up bits of something, a quantity or a little piece of volume or a little strip of area, and then we sum all those up to get the total quantity, the total volume of the total area, right? So this is this really important principle. Okay, and this is the same thing when we look at physics applications. All right, and so let's just talk about some basic physics tools. So in terms of doing these physics problems, we have to have some basic physics under our belt. So let's just review some of those things. So the first is work. In fact, all the problems we're going to be doing here up front are going to be work problems. So what does work equal in its simplest form? Who remembers physics? Force times distance. So work is the amount of force that you apply over a distance. Okay, so it's force times distance. Okay, and then the question is, what if this force is a function of how far you've gone? So the force changes along the distance. Right? So this is an easy formula. If you have a constant force and a set distance, right? So you're going to apply the same force over the distance. Well, you just apply that force times the distance and you get the work. Well, what if the force is changing as you go? What if the force changes as you go? How are we going to find the total work? Sum up
all of the forces.
Sum up the forces?
Or whatever you were saying, I got lost my train
Sum
of
up the product.
thought. Repeat what you said and I can answer you.
What are we going to sum? So we want to find the total work, and the force is changing as we cover this distance, or whatever thing is moving covers this distance. The force is changing. We want the total work.
Sum up all of the forces times distances.
Right. So you're going to sum up. So the total work will be the sum of what? Okay, but you don't, no, little bits of work. Yeah, which is, you're saying force times distance, but you're going to sum up the little bits of work. Okay, so for a spring, the force needed to hold a spring at a certain displaced length. So this is the force required to hold the spring. This is the displacement from its natural length. So it's the change from what it would be if it weren't being stretched or smushed. Okay, so this is displacement from natural length. So if it's at its natural length, what is x? If it's at its natural length, then what is x? And what's the force? Makes sense, right? So it's lying on the table or just hanging from the ceiling or whatever the spring is. If the displacement is 0, then the force is 0. That should make sense. It's when you pull it from its natural length that now there's forces involved.
Which one takes the positive sign, the pull or the push?
It's however you define it, but normally pulling it is positive, I think, and pushing it is negative, right? Yeah. But you, in a given problem, you can define it either way as long as you're consistent, and it'll.
Okay.
Yeah. I think conventionally pulling it is positive. Okay, K is called the spring constant, so it's a. This is a number that reflects how strong or stiff the spring is. So if K is really high, that would be like a strut on your car wheel, right? That would take a lot of force to get that thing to move, right? A very low spring constant would be like a slinky, right? Slinky, you just barely pull it and it comes apart. You know what a slinky is? It's toy, right? It's like that. Okay. So most springs would be in between, somewhere between a slinky and a car strut, okay?
Your unit of measure.
Yes, so that will be what? That would be force per distance, right? So in, so let's talk about, let's see. Yeah, so force is in, let's talk about units. So units of force. In the metric system, units of force are newtons. And in the English system, pounds, just pounds. That's work. You're saying work. So K would have units, newtons per meter or pounds per foot. In order that the displacement times the constant would give you force. Okay, so there's one kind of thing that kind of confuses students is this deal with force and weight and mass, which it's kind of it's different in the English versus the metric system. And in all these problems that we do in the next 3 days of class, this issue will come up because some will be in the metric system, some will be in the English system. So let's talk about that. Can I erase this? Okay, so force and so F equals mg. This is our this is for weight. So force equals ma. That should all be familiar. But for weight force, we use the acceleration of gravity. So it's the same equation, but we know specifically what that acceleration is. So what is g? G is 9.8 meters per second per second. That's how much a falling object will speed up every second. Every second, the speed will increase 9.8 meters per second, or 32.2 feet per second every second. So this is obviously metric, and this is English. Okay, so here's the thing. In the metric system, we delineate between, so mass is in kilograms, and then G is meters per second, and then that whole thing equals newtons. So newtons is weight, because weight is a type of force. Weight is a type of force. So newtons measures weight. Okay? Kilograms measures mass. So sometimes in these metric problems, you're given kilograms and you want the weight of it, not the mass of it. So you need to multiply by 9.8 to get the weight. Okay, but in the English system, it's not common to work with mass. You just work with weight, pounds.
Can you explain how those units collapse into weight?
Newtons is a measure of weight because weight is force. So this kilogram meter per second is newtons, and weight is a type of force.
Okay.
So that's basically okay. But in the English system, we don't have this delineation between you never given mass in the English system. Okay, that if you did, it would be what's called slugs. It's just like not conventional to use it at all. Slugs is mass in the English system. So instead, in the English system, you're just given pounds, which is weight force. So you don't have this multiplication where if you're given mass in metric, you multiply by the 9.8 to get the weight in newtons. So in English, mass is, I guess, unused. Weight is given. Weight force is given in pounds. So oftentimes in these, what I'm trying to tell you is oftentimes in these metric problems, you have this extra step. They're going to give you kilograms. What you need is force, weight force. So you'll have to multiply by G to get weight force. When the problem is in English, you don't have that initial calculation because you'll just be given pounds. You'll be given weight force. You won't have to multiply that by 32.2. It's already multiplied by 32.2. So the mass is not in play. Okay? So they'll just give you pounds, which is your weight force in English units. Does that make sense?
Why are you saying we need weight force? Like you just anticipated that the problem will do?
Yeah, lots of these problems will involve the weight of something. Yeah. So
are weight force and weight just the same term?
yeah. Weight, so just always remember, weight is a type of force. So therefore its units are either newtons or pounds. If you're in a problem that has the metric units and they give you kilograms, then you're going to need to multiply by 9.8 to get the weight force in newtons. That's what I'm saying. But if it's an English problem, it will just give you the weight in pounds. Okay, so let's and a big element to these types of physics problems is that you can take these tools of the trade here, these tools of physics, along with your understanding of an integral, and you can put it together and you can answer the questions without me doing an example first. That's what we're after, because then when we get to the exam, I'm going to give you an entirely new context, okay, that you've never seen before, and it's can you solve the problem using all these principles. All right, so it's less about, okay, here's the typical spring problems, and here's how you do those, and then here's the emptying a tank problems, and here's how you do those. So you got to think of each one as its own problem that you're setting up from your understanding. Okay, so why don't you try this problem here? There we go. See what you can do. See if you can do this by yourself. Or together. You can always work together, okay? Unless I say otherwise. Trying to get the total work.
So we need to get the force in the second part of the problem.
How are we going to find the total work if the force is constantly changing?
We need to make the dW.
We have to find a little bit of work. So the only thing we can get is a little bit of work. And then add them all up. We can, so this is what? Find a typical amount of work. Find a typical amount of work. It's going to take along the way. And we're going to add all those up.
You're not allowed to solve it. Wait,
No, you need to solve K.
K has an X.
You need to have that first. So what is K?
8.
8 what? Newtons per centimeter? Okay, so 8 is our K in newtons per centimeter. Yes, you need that, definitely.
But then the work equals force times distance.
That's right.
So we have to multiply by another X.
Right. So how are we going to conceive a little bit of work along the way from 10 to 15 centimeters? Or actually, we're going to go from, our X is going to go from 15 to 18. Okay, so along the way, we need to conceive of a little bit of work.
Delta X
Delta X times
times force.
force, right? So a little bit of work, so a typical bit of work.
Oh, okay. This is cool.
This is, again, we're going back to the same thing we did before. Typical bit of work is going to be a delta W. And delta W is going to be what? Force times. And how far of a distance will we be going for a little bit of work?
Just a chunk of delta X.
A small amount. Why? Because as soon as X changes, the force is changing. So we gotta do it for a small change in our length. So what's the force? No? We're getting a typical bit of work here. What is our force? What's our force?
Delta W over delta X.
No.
Oh. 8X.
8x. 8x. That's what we found, right? The force to hold this spring, a displaced amount x, is 8x. And then the work is going to be just the little change of distance that we do times that 8x. Okay, so now what's the total work? So we got our typical bit of work here. So then what's the total work going to be?
We can integrate from 15 to 18.
Is it going to be from 15 to 18?
0 to 3, 5 to 8.
What does x represent?
Change from its equilibrium.
Displacement from natural length. So x is going to go from what to what?
0 to 5 to 8.
5 to 8.
Wasn't it?
Its natural length is 10. So we're going to stretch it from 15 to 18. That means the displacement is from 5 to 8. X value is from 5 to 8.
I don't follow.
Its natural length is 10. We're going to stretch it from 15 to 18. But x is the displaced length.
What's it display?
So x is not the total length, it's the displaced length. So when we stretch the spring to 15 total centimeters, its displaced length is 5.
Okay.
And at 18 centimeters, its displaced length is 8.
It's as if we were changing the limits for u substitution.
Kind of. But, I mean, it's a little more... You could think of it that way, but you don't need to.
Yeah, it's solid. Okay, gotcha.
Okay, and then we're going to sum up what? What are we summing up? Each little bit of work, which is 8x dx. And that will be, now the units we're using here are newtons and centimeters. So when you work this whole thing out, you get, that's a very easy integral. That's 156 newton centimeters, which would be how many newton meters? 1.56. And the reason we want newton meters is because newton meters is joules. Joules is the same as newton times meters.
Wait, so then work is energy.
It is. Work is energy. That's right. When you do work, you give it that. When you do that amount of work, you give it that much potential energy. So we've added, by stretching the spring from 15 to 18, it took this much work, and we just gave the spring that much potential energy, 1.56 joules. Okay, so you see, it's the same thing as the volume problems. It's the same thing we've been talking about all semester. You get a typical little amount of whatever you want the total of. In this case, that was 8x delta x, was a typical little bit of work. And we can't have a big delta x. Why? Because as soon as you change that spring length a significant amount, your force is changing through that. Right? So we just need a little change in the spring, and we just assume that the force is 8x for that whole little change, and then we add them all up. Add up all the little bits of work. Okay, another example. I can't get to my play bar. Okay. Here we go. So a 20 kilogram chain hangs 30 meters from the roof over the side of a tall building. How much work is required to pull up the entire chain to the roof? So let's draw a picture. Like that. So initially, so this is 30 meters here. This is the chain. Okay, and so that we're all on the same page, we're going to use our x is going to be measured down from the top of the building. So x is going to be measured down from the top of the building. So now force is not going to be Weight is force. Weight is force. It's not force divided by distance. It's not force times distance. Weight is force.
Weight equals force.
That's true.
Force.
If we can get the weight of X meters of chain, and then what are we going to multiply that by? To get the little bit of force, a little bit of work.
30 minus X.
No,
X.
nope. To get a little bit of work. Typical bit of work is going to be
196.
right. So delta W is going to be
196.
force times a little movement upward of the chain. Right? Because as soon as you move the chain up a significant amount, what happens to the force? It decreases, right? As soon as you move it a significant amount, you have a different amount of force now, weight force. You have less weight. Okay? So we need just a little change. So we have X amount of chain hanging, and we just going to move it up a little bit, delta X, and we need the work required for that. So work is force times distance, and so this force is then the weight of X meters of chain over the building. So what's the weight of X meters of chain hanging over the end of the building? If 20 kilograms is 30 meters. 20 kilograms, 30 meters is 20 kilograms, which is how many, what weight is that? 196 newtons. That sounds like a good conversation there.
196 over X, right?
196 newtons. That's the total weight of the chain. So how many newtons does X meters weigh? 30 meters weighs 196 newtons. How much does X meters weigh?
Oh man. 294.
2 kilograms per 3 meters.
Okay.
196 X.
No. We'll try it. Okay, so 196 times 30.
And then over to
Is that the weight of 30 meters of chain? No. 196 is the weight of 30 meters of chain. Yeah. I got that correct.
X times
It's force.
So you guys were finding a very important feature there. What did you find that?
To find the weight of the chain at any length, just took 20 kilograms over 30 meters, and that gives you the weight of the chain in kilo.
So 196 newtons over
No, I
30 meters gives.
20 kilograms over 30 meters. Oh, okay.
Okay,
And then got 2 kilograms for 3 meters, or whatever that is in newtons.
so really we want to know how much 1 meter of chain weighs, right?
Oh.
How much does 1 meter of chain weigh?
6.5.
Gene, is that what you got?
6.53.
6.53 newtons per meter. So, yeah, this is the weight of 1 meter of the chain.
Oh, okay.
Yes, it's a weight, but a weight of just 1 meter of this chain. Newtons per meter. The total weight is 196 newtons. This is also a weight, but just of 1 meter of the chain. So therefore, what's the weight of X meters of the chain?
196.5 grams.
Right. Or 196 over 30 times X. So you get the weight of 1 meter, and you multiply it by the number of meters, which is X. And that at any given length X, that's the force required to pull it a little bit, because it's the weight of the chain hanging over. Okay, so that's our little, so what's our little bit of work? Typical little bit of work is, delta W is?
6.53 x delta.
That's it. Therefore, total work is?
Integral from
0
0 to
to 30.
6.5.
Yep. Which is our force at a length of X times a little change in distance. That's our little change in work, and we're going to add up all those little changes in work from 0 to 30. Okay, let's add a new twist on this here. Okay, so now it's pulling a bucket. Okay, so the key to this is, what's the total mass of everything at 30 meters? What's the total mass of everything at 0 meters? And then from those, you can figure out what's the total mass of everything at X meters. And then there's nothing different than the last problem. What's the total mass of everything at 30 meters? 45 kilograms. What's the total mass of everything at the top? How much for the chain?
5 plus 0, 5.
0 for the chain, 0 kilograms for the chain, plus?
Oh, you gotta add
5.
So then here's the big question. When X meters is hanging over, what is the mass, the total mass when X meters is hanging over? Can you figure it out?
That's just gonna be 40 plus 30. About 5 plus 4/3 X.
He wants 5 plus 4/3 X for the mass at X meters. So this is a really crucial skill for these problems. So everyone take a break here. Take a break and look up here. This is a huge skill that you're going to see over and over in these problems. If you can't do this, then you'll bomb these problems. What kind of relationship is that? Linear. Hear me now. You need to be able to develop linear relationships, linear functions, in order to solve these problems. So I set you up. I said at 30 meters, the total mass was 45. At 0 meters, the total mass was 5. And it's spilling, and the sand is spilling out at a constant rate. So to get the total mass at X meters, you need the linear relationship that comes from this data. Many of these problems are where you'll have to do this. There's different ways to do it, but just as long as you have a way that you can get this. Okay? So at 0 meters, 5 kilograms. At 30 meters, 45 kilograms. Therefore, at X meters, how many kilograms? So the rate of change is 45 minus 5 over 30 minus 0. Change in mass over change in X. It's your rate of change, which is 4/3. Right? Change in mass or change in Y over change in X. Slope or rate of change.
We need our M naught.
At 0, you have 5. Therefore, what's the total weight at X meters? Therefore, the total weight or force at X meters is?
13.07.
No, it's going to be M times G, right? So here's your M. So it's going to be that times 9.8. That's your mass, right? So a little bit of work. It's going to be delta W equals F times delta X. F is the weight of X meters hanging down.
5 plus 4/3 X times 9.
Right, so it's going to be M times G. There's your force times delta x. That's your little bit of work that's going to be required when x meters is hanging over the building.
So then we just integrate.
Yep, so then total work equals?
Equals 0 to 30 of the expression.
Integral from, x is going to go from 0 to 30. So a huge part of these problems is going to be your ability to recognize and develop a linear function. You recognize that, oh, I need a linear function here. When x is 30, I need my linear function to give me 45. When x is 0, I need my linear function to give me 5. So therefore, if my length is x, what linear function gives me that corresponding mass? Change in y over change in x is your rate of change. And in this case, your intercept, right, when x is 0, your output is 5, so you have plus 5. So mx plus b.
Cool.
That's your mass, and so then the weight is, or the force, times 9.8. And then you got force times a little change in distance is your little bit of work, and you're going to sum up all those little bits of work from 0 to 30. So again, you've got to, in these problems, you've got to recognize and be able to create linear functions.